irreversible by molecular type second order reaction. So it's a second order. What's the specific particular form for this second order reaction? So we consider if it is an elementary reaction, A react with B, then we will generate products. So the consumption rate of reactant A can be expressed like a minus dCA over dt. And as you know, we consume one A with one B, right? So we can equals to minus dCB over dt. Because we consume one A, we will also consume one B. This is elementary, okay? Then we will get the KCA to 1, CB to 1 because this is a second order reaction. So next we are going to find how to express the Ca. So what's the Ca? Is the initial concentration of reactant A minus the reacted portion. So reactive portion will be expressed like a Ca0 times the fractional conversion. Fractional conversion means how much a fraction be converted to product, right? So you use times the Ca0, so you will get the reacted portion. So Ca0 minus the reacted portion, you got a Ca, right? And Cb, how to express the Cb? Cb is Cb0, the concentration of reactant B at time 0 minus the reacted portion. And this reactive portion, we know consume 1A, also consume 1B, so we use the same expression way as this one. So we got the expression for Ca and Cb. So we are going to use this and this term to substitute Ca and Cb. And also we also have a Ca0. So we take a Ca0 out. So we got Ca0 squared and also 1 minus Xa, Cb0 over Ca0 minus Xa. So we got this term. And for the left-handed side, dCa, you also can express as Ca0 times dXa. Why do d minus dCa, Ca0 times dXa. Okay. So now we get this equation, right? And if you take a look on this equation, you got the Xa. So we need to move left to the left-handed side dt to the right-handed side and take the integral, right? But here we can simply find one thing is this term is really special. This is the initial concentration ratio between the B and A to A over the A. So we use the M to substitute it. So we can, based on the value for the ratio between B, concentration Cb0 over Ca0, we can simply separate into two cases. The first one is if M is not equals to 1, that means the initial concentration of reactant B and A are not the same. In this case, we will leave the M here, right? So we need to also move this to left-handed side dt to right-handed side and take the integral. So after series deviation, the detail you can check on the page 77 to 75 in lecture notes. And you got this relationship for when M not equals to 1. So if it is a case, then if we use this as a y and this is a x, then the data you put in, if you got the straight line, then you will say, oh, this reaction we're talking about is a second order reaction, irreversible second order reaction. Okay, if it's not the straight line, then that definitely not the irreversible second order reaction. The other cases will be the simple one is if M equals to 1, that means the initial concentration of A and B are the same. So 1 minus Xa. So this you can consider Ca0 squared 1 minus Xa. 1 minus Xa, you take a square here. So move this term to left-handed side dt to a right-handed side, take the integral. So finally, you will get the relationship. It will be here. So if you use this as a y, this as a t, then you got a straight line. Then, oh yes, the chemical reaction you deal with is a second order reaction. Okay? Okay, so the third one will be the zero order reaction. So zero order reaction, the rate of these zero order reactions do not vary with increasing or decreasing reactants concentration. So when you write down the zero order reaction, becomes like this: KCA0, so be equals to K. So as this rate constant, consumption rate of reactant A is nothing related to the concentration of reactants. And you also move the dt to here and take the integral on both sides. So this is integral method, so always we take the integral, right? Then what we got is this results. And CA0 minus CA is the what? Fractional conversion XA times CA0. So if you try to plot the CA as a function of t, CA as a function of t, then the slope you got will be CA0 minus, or slope will be minus k, right? And if you try to plot XA over t, then slope you got a k over CA0. Okay, so some people probably will ask what kind of situation we deal with will be belongs to zero order reaction. So there are two general conditions for zero order rates. Is only a small fraction of reactant molecule in specific locations which are able to react. Not whole portion, not all reactants molecule, only small fraction of reactants can be react. And this fraction is continually replenished from a larger pool. And the second case's general condition is also similar with this one, is when two or more reactants are involved, the concentration of some are much greater than those of others. So the limited step will belongs to the small or fewer numbers of reactants. The small one dominate everything. So I'm going to give you an example to explain the zero order reaction. What's the only small fraction of reactants can be react? So I'm going to give you an example here. We have a decomposition of nitrous oxide, and this general chemical equation or chemical reactions can be performed at 575 degrees C at this high temperature. But if you want to decrease the temperature or want to speed up this reaction rate, as you know, you can end the catalyst to lower the activation energy, right? So the catalyst here we use would be the hot platinum wire. So because this hot platinum wire serving as a catalyst, so this reaction, this catalyzed reactions or catalyzed decomposition reactions will belong to zero order. Why? Because although I have bunch amount of nitrous oxide, but only small portion of nitrous oxide which adsorbed on this platinum wire can be decomposed into nitrogen oxygen. So this is limited available site on this platinum wire. So as long as this one be decomposed, then there will have available site to allow the other nitrous oxide to adsorb on it, then it will continue to be decomposed, right? So in this case, N2O molecular reactors are limited to those that have attached themselves to the surface of this catalyst. As long as all the sites on the limited surface of the catalyst has been occupied, so additional gas phase, additional nitrous must wait until the decomposition of one adsorbed on the adsorbed molecule free up a surface site. Okay. So in this case, only small fraction of reactant molecular nitrous on platinum, this catalyst are able to be decomposed. Okay, so I'm going to give you the other example to show you how to get a reaction order and rate constant by integral method. I already limited the method you only can use is the integral method. So now we have a sulfuric acid react with diethyl sulfate, then we'll generate this product. And we assume the initial concentration of the reactants are the same, so we know m equals to 1. And we measure, for this experiment, so we can measure the concentration of products as a function of time, from time 0 to infinite. So next, actually we already know the relationship between XA and T versus T for 0, first, and also second order. We know a particular form, right? So XA is quite important, but now we only have CR, the concentration of products. So we try to convert the CR to XA. Okay, so the XA defined as a fractional conversion, so it's 1 minus CA over CA0. So we got the CA0 minus CA over CA0. So what's the CA0 minus CA? CA0 minus CA is the how much concentration of reactant A be converted to product, right? So it can be, and if you consume one reactant, you will generate 2 products. So it's a CR over 2 here, because we got 1, and you generate 2. So you used to your CR to substitute it will be CR over 2. So now we already know the CR. And what's the CA0? As long as we know the CA0, we can successfully convert this data as XA, right? So what's the CA0? It's the initial concentration of reactant A. Will be what? Check infinity. At time infinity, we got the concentration product is 5.8. 5.8, so you got a 2.9 in the beginning. So as long as you know this, you can successfully get the XA as a function of time here. So as long as you got XA as a function of time, then we can use this data. Then we input in this particular form for 0, first and second order. We know XA over as a function of t, right? Then we use this as a y and this is x. Then we put out, this is not a straight line, so this reaction not belongs to 0 order. And this is a particular form for first order. We input xa and t, then use minus log 1 minus xa as a y-axis and t as a x-axis. I get a straight line. And for the second order, this is a particular form, and use this y and this is x. Then I get a curved line, so this not belongs to second order. So it turns out that this reaction belongs to first order reaction, because when I use this as a y-axis and this is x-axis, and I got a straight line, and the slope belongs to rate constant. So now I know the reaction order is 2, and the rate constant is the slope here. So this is how we use the integral method to get the reaction order and also the rate constant. So now I'm going to give you something, an example or homework. I have a liquid A and decompose irreversibly, and we know 50% of A is converted to the product in 5 minutes. And how much longer will it take to reach 75% conversion? So 50% of A converted to product. So I tell you the XA is equals to 0.5 and T is 5 minutes. So how much time it takes to reach 75% conversion? So it means XA equals to 0.75. What's the time? So because we don't know the reaction order, so we need to separate. We need to assume probably it is zero order reaction. So in a zero order reaction, as long as you want to express the relationship between XA and T will be like this, right? Then you can get the T will be 7.5 minutes. And for the first order, you can get this is first order, so you just move Ca to left hand side dt and take the integral. Then you can get this particular form. Then you input this 0.5 and 5 and over 0.75, and this is T you are interested in, so you can get 10 minutes. For the second order, actually directly we assume m equals to 1, so we can get this, and after input you also get, because we can input this, right, and you can get 15 minutes to have a 70% of conversion. Okay. Okay, so we find a specific particular form for zero first and second order rate equation. As long as you measure the concentration as a function of time, or fractional conversion as a function of time, then you can input all the experimental data to check whether your reaction belongs to first, second, or zero. So next we are going to show you regarding to the parallel serial reactions. How can we get the rate constant for irreversible parallel and serial reaction, and also a reversible first order reaction? So just give you a remind, when we talk about a parallel reaction, how can we know whether our experiment is parallel reaction? Usually, first thing you will do will be you measure the rate equation at different temperature. Then you got, if it is straight line, just one chemical reaction involved. But if you got this curve, and after fitting you got this reaction must involve two chemical reactions, and with two different activation energy, and at higher temperature the reaction 1 dominate, and at low temperature reaction 2 dominate, but both of is the fast path dominate. So the relationship between reaction 1 and 2 definitely is a parallel reaction. Now they are parallel reaction. So what's the K1 and K2? So that would be, you need to design experiments to know the K1 and K2. So how to determine the K1 and K2 in irreversible parallel reaction? So now we have, this is a first order, and we have the A generate R with rate constant K1. Or there's the other possibilities, A generate to product S with rate constant K2. So when you try to write down the consumption rate of reactant A, it can be expressed like the sum. You need to sum all the consumption rate, right? So it'll be the K1 Ca plus K2 Ca. And you take the K1 out, or Ca out, you got the K1 plus K2. Before we move forward, don't forget it, because you have two unknown parameters, K1 and K2. So you need to have two equations, then you can get K1 and K2, right? So now we successfully get the one equation. So we still have the other information haven't been used. Is you also can measure concentration for product R and S, right? So dr over dt is K1 Ca, because one mole generate 1 R, and Rs also dCs dt is K2 Ca. If you divided this with this, you got the dCr over dCs, you got K1 over K2. Okay, so first of all, we deal with this one. We move the Ca to left hand side, dt to right hand side. We take the integral, so we got this relationship. And the second one, we also organize or arrange it. What's a dr? CR, that means CR minus CR 0. The CS considered CS minus CS 0 then equals to K1, K2. So now we have two equations and we also have two unknown parameters. So we have chance to get what's the K1 and K2. So next is how to do that. So first of all, we need to plot two figures. The first one is use this as a Y and T as a X. Okay? And the second one is you plot the CR over CS. And the slope, this slope will be K1 plus K2, and this slope will be K1 over K2. Because you use this over this, right? So doing the experiments, T1 you can measure CA, got this one, and also you can measure CR and CS, so you got this point. And at T2 you can measure CA, CR2 and CS2, you got this point. And term 3, CA3, CR3 and CS3, you got this point. So after fitting, we know the K1 plus K2 and also K1 minus divided by K2. So you can get the K1 and K2 in your experiments. So this is how we determine the K1 and K2 in irreversible parallel reactions. But don't forget, you need first of all to determine whether your reactions belongs to parallel reaction. You need to measure the log R at different temperature. Then first of all, you need to know this. Then you can determine the K1 and K2. Okay. Okay. So next, I'm going to give you the other example. It's also a parallel reactions. Is a homogeneous catalyzed reaction. Usually people will enter as I mentioned, will enter the catalyst in their chemical reactions, right? And to provide the other path with lower activation energy. So the idea will be like, so in this beaker, you do have two paths, chemical reaction paths, right? So the first one is A generate R with K1, and the second path will be the A plus the catalyst generate R plus the catalyst with rate constant K2. For this one, usually the energy barrier is smaller than this one. So when I try to write down the consumption rate of reactant A, can be, in this case, would be K1CA. In this case, it will be K2 CA, and also times the CC is a concentration of the catalyst. So here we demand the assumption is consumption rate of reactant A is proportional to concentration of catalyst. Okay, so we sum the consumption rate. We got the total consumption rate of reactant A can be expressed like this. We take the CA out, and then we got the K1 plus K2 CC. And also we move the CA to a left-handed side, dt to a right-handed side, and take the integral on both sides. Then we will get this results. K1, K2, CCT, right? And use this as a Y and this as a T. Then the slope will be like this, right? So how to determine the K1 and K2 in this catalyzed reaction? In the beginning, I don't end the catalyst. Then I measure CA as a function of time. Ding, 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 ding. 4 different time points. Then I can get the K1. Next, as long as I know the K1, and also I get the K1 here, right? Because K observed is a K1. And this is a K observed versus the CC. So now I ended a small amount, probably 1 more of CC. Then I also measure the CA at 5 different time points. 1, 2, 3, 4, 5. So after fitting, I got a slope. This slope belongs to what? It's a K1 plus K2 CC. The slope is here, right? So I got here. K observed is a total slope, and the horizontal is a CC concentration 1 more. Or 1 more. right? And I also try to increase the CC again to 2. And I also got to this point. Then after fitting, I already know K1, so this slope belongs to K2 because we use the K observe to versus CC. So after fitting, this is a K2. So this is how we get the K1 and K2 in the homogeneous catalyzed reaction. Okay, so today we ended here.